All right, hi everybody. We're looking at the 2005 E&M Problem 1, which gives us a two-dimensional electric field lines chart that we're to analyze and do some basic problems with. So um, let's go ahead and get started. So for part A, we have points A, B, and C located along this axis at 0.06 meters on the x-axis, or excuse me, the y-axis, and we're asked to compare the magnitude of the electric field and figure out where it's the greatest. The basic rule with electric fields is that where the field lines are closest together, so in this region, you have the highest or the greatest magnitude of the electric field. Um, and so the answer to part A1 is C, and the reason for that is that the field lines are closest together. So that's the first part of the problem. All right, for the next part of the problem, we're to look at this same chart and determine where the electric potential is the greatest. Now, electric potential, you'll recall those lines are perpendicular to the field lines at all points, and so they're going to travel something like this along these lines, perpendicular to each of the places. So when we're thinking about the electric potential in part B, we have to remember that electric potential goes from where the field is positive to where it's negative. And so remember, fields go from positive charges to negative charges. So if we were to draw the field lines for something simple like this, it would look like that. And the place where the field is most positive is at A, so that's where the electric potential is greatest. Um, and as we move towards B and C, the potential drops. All right, for part B, we have an electron released from rest at point B, and we're supposed to just qualitatively describe the electron's motion in terms of direction, speed, and acceleration. So it goes from here at B somewhere. So electrons have negative charge, which means they go in the opposite direction of electric field. So an electron released at B is going to head towards A. So that's the first part of the question. So the direction is to the left. All right, and the speed, any electron interacting with a field is experiencing a force, because remember, force just equals Q times E. So the charge here being the electron being in the field means that it's experiencing a force, which means it's accelerating the whole time. And if it's accelerating the whole time, so that's for direction. If it's accelerating the whole time, the speed is increasing. So that's the next part, because there's acceleration. Now, as we said before, the field is highest at C, and it gets weaker as we go towards A. So the acceleration, even though it's positive, is decreasing. Okay, so now we're on to the next part. If we're calculating the electron speed after it's moved through a potential of 10 volts, here's how we do that. So when we use potential to figure out velocity, and especially in a situation where we have non-constant acceleration, we have to use conservation of energy. All right, so to figure out the potential energy of the electron, we use U equals QV, and that's going to be equal to the kinetic energy after 10 volts of potential change. So that's going to be equal to 1/2 mv squared. All right, so then we just solve for V. The little v, big V is the potential difference, so I'll put a delta in front of it to distinguish it. So that's going to be equal to the square root of 2 times Q times delta V divided by the mass. All right, and then we plug in our known values, so V is going to be equal to the square root of 2 times 1.6 times 10 to the negative 19th coulombs, which is the charge of an electron, times 10 volts, times the mass of the electron, or excuse me, divided by the mass of the electron, which is going to be 9.11 times 10 to the negative 31 kilograms. All that's available on your handy equation tables and data tables. And when we solve that, we get a velocity of 1.9 times 10 to the 6th meters per second. I'll leave that up for a second. Okay. So for part C, we're asked to figure out the magnitude of the electric field between B and C, knowing that B and C are separated by a potential difference of 20 volts. Okay. Alright, and then we have to state some assumptions that we make. So field, electric field, just equals negative delta V over distance, which we can express as R. And in this case, if we look at our picture up here, we have to estimate the distance between B and C. And so that distance looks like it's about 0.01 meters. So in this case, it's just 20 volts over 0.01 meters, which gives us an answer of 20,000 volts per meter. Now, depending on the direction of our radius here, it's either going to be a positive or negative 2,000 volts per meter. It's not 20,000 volts per meter, excuse me, it's 2,000 volts per meter. So either way, we can say it's just 2,000 volts per meter here. Alright, for part D, we're supposed to sketch an equipotential line that passes through point D and intersects at least 3 electric field lines. Alright, so here's point D. Now, we have to remember that potential lines are perpendicular to field lines, so that's basically what we're going to try to estimate here. Since we have some curves going on, we're just going to have to do our best with it, but I would estimate that that's about perpendicular to that line there. Curves up, perpendicular again, curves up, perpendicular. So we get something like that, and then we have at least 3 field lines intersected. And that's all we got to do.